Hello, today we're going to take a look at what we actually do with those quantum numbers now that we know what the four of those values are from a previous recording. And that just happens to be writing electron configuration. So let's talk a little bit about how we go about doing this. Well, the old way of doing things actually looks something along the lines of this, where you had the nucleus in the middle, and then you had rings coming out. And most of you remember doing this. And the rings coming out from the nucleus were numbered. We now know those to be energy levels. But when you used to draw models of the atoms, you guys probably did something like this. You put 2 electrons on the inner ring, and then 8 on the next one, and then 8 again. And you kept going until your atom was complete with the number of electrons that was needed to show that atom. Well, that's the old way of doing things, which is a nice representation, but is not entirely correct. The new way that we take a look at this is if we think of the atom being in space and being a three-dimensional system where in the middle is still the nucleus. Then what we've got is we've got these outer limits of the area defined by Schrodinger and Heisenberg's mathematics and some other individuals, but we don't really talk too much about the math that does this. But for example, this area, which still on that innermost circle would be numbered the first energy level and then the second, is actually thought of as a three-dimensional cloud. So there's actually a sphere there of space if it's a certain shaped cloud, and within that area 2 electrons might be found. That's the most number of electrons that we can have in there. And so the new way of thinking about this aren't these rings where the electrons reside, but it's these areas in space, these clouds, if you will, or sublevels, that the electrons have a high probability of being found in. So in order to do this correctly, we have to do what I would kind of call a review of subshell information. And the subshells are S, P, D, and F. Now, if we look at that, the energy levels where they're available, in order to have an S subshell, N has to be greater than or equal to 1. So we have to be in the first energy level. To have a P subshell, N has to be greater than or equal to 2. So we have to be the second energy level from the nucleus. For the D subshell, N has to be greater than or equal to 3. And then for the F subshell, it's got to be greater than or equal to an energy level of 4. Now the maximum number of orbitals that we can have on this, which would be the different axes of orientation, happens to be the odd integers. So we'd have 1, 3, 5, and 7, and those come from the quantum number values. So that means that if we've got an S-shaped orbital, or the predicted space, there's only one shape that can be, and it happens to be a sphere. If we have a P-shaped orbital, there's 3 suborbitals that we can have, one on the x-axis, one on the y-axis, and one on the z-axis. And then if we have the D's, there's 5 possible orientations, and then the F, there's 7 possible orientations. Well, we're going to come to find out that 2 electrons can fit in each one of those orbitals. So that means if we're talking the S subshell, we can have 2 electrons in there. If we're the P subshell, we can have 6, since there's 3 orbitals and 2 electrons fit in each. And then 10 and 14. So those are the maximum number of electrons that can fit in each one of those subshell shapes. So that's kind of a real quick review about subshells, and we can talk more about the quantum numbers. You know, if you need some help, come on in or sit down with one of the chemistry teachers here and just ask us for a little bit of help. Now, when writing electron configurations, there's a set of rules that you have to follow. There's 4 main rules. So these are the rules for assigning electrons to the different orbitals. Number 1, electrons will fill the lowest energy level first before continuing. So they'll fill the first energy level, N is 1, and then 2, and 3, and hopefully you see the pattern. But at some point you should probably pause this podcast and write these rules down. The second rule reads, for subshells, the electrons will be assigned a location based on the lowest energy first. So we go S, then P, then D, and finally F. The electrons will follow the Pauli exclusion principle, which basically states that no two electrons may have the same set of 4 quantum numbers, otherwise they'd have the same address. And then 2 electrons may fill a subshell as long as they have different spin values. And then we talk about the fourth rule, and that's that the electrons will follow Hund's rule, which essentially states that electrons will occupy all the orbitals of a given subshell singly before pairing up. And then these electrons that fill singly have parallel spins, and we'll take a look at that. So rule number 1 in detail. Electrons fill the lowest energy level available first and then continue. So if we draw our 3-axis system and we put on here the energy levels described by quantum mechanics and we number them outwards, the electrons will always fill closest to the nucleus before continuing on. So we fill the first energy level and then the second and then the third. Rule number 2. For subshells, the electrons will be assigned a location based on the lowest energy first, S, then P, then D, and finally F. So what happens here, for example, is you end up with a filling order of the orbitals or the clouds or a certain sequence to which they fill. So you'd start with the first energy level and the S shape, and then we'd have the second energy level S shape and the second energy level P shape, 3S, 3P then, 4S, 3D, 4P. Now in this sequence right here, you'll notice that the 3Ds are kind of stuck in the middle there. Your book shows an alternative approach to this, and you might take a look at that, but you can see kind of the pattern that we have here as we go through and do this, and we'll talk more about it as we get there. The Pauli exclusion principle. So you might think back to the quantum numbers, and the last quantum number is n sub s, which is the spin of the electrons. I'm sorry, m sub s, which is the spin of the electrons. And we can have 2 spins, positive 1/2 or negative 1/2, which basically tells us that the electron is spinning opposite directions, 2 different rotational motions, if you will. So that tells us that only if we vary that number right there can 2 electrons fill an orbital, because they'll have a different set of quantum numbers. So that's what we end up seeing there. And then Hund's rule. What we see with that, for example, is if we have, let's say, the P-shaped orbital, there are actually 3 orientations for that, and I'm going to show that with a dashed line. There's the X, the Y, and the Z. Now let's just say that we have 1 electron to put in there. So if it's spinning with a positive 1/2 spin, just arbitrarily, I'm going to use an up arrow to show that. And if it's spinning with a negative 1/2 spin, I'm going to show it with a down pointing arrow. So what we get here is we get this. If we only have 1 electron to put in there, we would have an up arrow pointing that direction on the X orbital or the X orientation, and it doesn't really matter which way we go. Now if we had a second electron to put in, what Hund's rule says is that one's going to go in the Y orientation, pointing the same direction. A third electron will go into the Z orientation, pointing this parallel direction as the X and Y. And then for our 4th electron, we go back and we pair them up. So there's the 4th electron, the 5th electron, and the maximum of the 6th electron. So that's how Hund's rule works. We put them pointing the same direction first before going back and pairing them up. So let's see if we can do this with some arrows. You might watch the first couple and then pause it and try the next couple and see how you end up. So hydrogen, excuse me, the element hydrogen is the simplest element on the periodic table. So we always start with the first energy level and the S shape, and with arrows, So the S-shaped orbital only has one orientation, so there'll be one line drawn above the 1s. Hydrogen contains one electron, so that means one arrow pointing either up or down, it does not matter. And that is the orbital diagram for hydrogen. It shows us that we have one electron in the 1s orbital, and it's spinning whichever direction it happens to be spinning. So how does that differ from helium? Well, helium has two electrons, so we start the same way, the 1s orbital, so there's one dash. Two electrons, one pointing up and one pointing down, and there is the orbital diagram for helium. How about lithium? Lithium has three electrons, so we start in the 1s orbital, one arrow up, one arrow down. That orbital is now complete, but we only have two electrons, so we need to go to the next orbital, which is 2s. Lithium has three electrons, so we just need a third arrow pointed either direction is acceptable. So as long as you have something along those lines, then you've got a correct orbital diagram for lithium. How about beryllium? Well, beryllium starts the same way. 1s, and there's two electrons in there, one up and one down. And then 2s, also a single orientation, so one dash, and one arrow up and one arrow down. There are the four electrons for beryllium. Let's take a look at boron. Boron starts the same way, 1s. There's two electrons in there, one up, one down. We have 5 electrons to show. And then 2s, one up and one down. There's 4 electrons. Next comes 2p, which has 3 dashes, but there's only one electron in there, and it doesn't matter the direction, but there is the orbital diagram showing the 5 electrons of boron. Carbon then, 1s with 2 arrows. We have 6 electrons to show. 2s, there's electron 3 and 4 up and down, and then 2p with 3 orientations. We have 2 electrons to show, so according to Hund's rule, they both point in the same direction, but they're in different subshells, or same subshells, sorry, but different orientations. So there are 6 electrons for carbon. How about nitrogen, which is a total of 7 electrons? 1s with 2 arrows, and then 2s with 2 arrows. There's 4 of the 7. 2p, so we've got 3 electrons to show. They all point the same direction, and there is what we end up with for nitrogen. I'd encourage you to pause this podcast right now and try oxygen and see what you end up with. See if you can predict based on the pattern. Welcome back. Hopefully you tried it. So here we go, 1s with 2 arrows, 2s with 2 arrows, and then 2p, 1, 2, 3, 4. And there are our 8 electrons in the oxygen atom. So that's how we do this with orbital diagrams. How about with electron configurations? Well, let's take a look at that. So electron configurations are written a little bit differently. Instead of arrows, let me show you what it looks like. So for hydrogen, our orbital diagram from the previous screen looked like this. So the electron configuration is written like this, 1s with a superscript 1 to show that there's 1 electron in there. This is where it's really important that you know the maximum number of electrons that can fit in each subshell. Because, for example, with helium, you end up with 1s2, since it has 2 electrons. What does this tell us? It tells us we're in the first energy level. For n is 1, the L value is s, and then there's 2 electrons in there, in that orbital. That's where they're likely to be found. So how about lithium? Well, we go 1s, and there's 2 electrons in there. That completes that 1s orbital, so then we have to go to 2s1. For beryllium, we've got 1s2, 2s2. For boron, 1s2, 2s2, 2p1. For carbon, 1s2, 2s2, 2p2. For nitrogen, 1s2, 2s2, 2p3. And for oxygen, 1s2, 2s2, 2p4. So the arrows simply become superscripts. Those aren't powers, but they're superscripts to show the number of electrons in each one of those orientations. So what I'm going to end this podcast with is a filling order. So the order for which the orbitals actually fill. So here's a filling order for the different electron orbitals. So we fill the 1s first, so the arrows point from right to left. 1s first, and then 2s, and then 2p and 3s, and 3p and 4s, and 3d, 4p, and 5s. So you can see the sequence by which this goes. And hopefully in class, we'll get a little bit more time to talk about this, and you can ask some questions. But you need to definitely take some notes and then come in and get some help on this. We'll talk to you in a little bit about how to use the periodic table on how to do this. So we'll see you again soon.